Think about it, you're soaring miles above the earth in something that weighs hundreds of tons. It really hits you sometimes. Airplanes are just incredibly complex machines, maybe some of the most complex ever built.
Oh, absolutely. It's true. When you actually stop and think about the scale, the precision needed, I mean, the journey an airplane takes from just an idea to its first takeoff, it's extraordinary, a real testament to human ingenuity.
And that's exactly what we're diving into today. We're going deep on how airplanes are actually made. From that very first blueprint right up to the moment it lifts off the runway.
Yeah, and we're not just talking small planes either.
No, exactly. We'll be looking at everything from those sleek private jets to the huge commercial airliners most of us fly on. It's quite a rigorous journey they go through.
It really is. So to give everyone a clear picture, we'll walk through the main stages. First, there's the design and conceptualization bit where it all kicks off.
The idea phase.
Then, crucial stuff, material selection and how they actually make the individual components. After that, we'll get into the assembly line manufacturing. Quite a sight, usually.
Okay.
Then installing the interior, making it passenger ready, and of course the absolutely critical testing and quality control.
Can't miss that.
Definitely not. And finally, how it gets certified and delivered to the airline.
Okay. Sounds like a comprehensive look. So let's kick it off right at the very beginning. Like you said, every amazing piece of engineering starts somewhere. Usually just as an idea.
Exactly that. It might seem basic, but before a single piece of metal is shaped, someone has to envision the aircraft.
And for the big manufacturers like Boeing or Airbus, that idea doesn't just pop out of nowhere, does it?
No, really. It's typically driven by identifying specific market demands.
Mm-hmm.
Airlines might be saying, look, we desperately need planes that burn less fuel. That's a big one, obviously.
Cost savings, environmental concerns.
Yeah. Or maybe there's a need for aircraft with longer range, connecting cities that weren't possible before. Or maybe it's about cargo, fitting more freight onto a plane. These kinds of demands really spark that initial design thinking.
So it's really about spotting a gap or a need in the aviation market. Once they've zeroed in on that need, what's next? Do they just start sketching?
Not quite so fast.
Mm-hmm.
The next really crucial step is conducting feasibility studies. This is where they dig into whether the idea is actually practical.
Practical how? Engineering-wise? Financially?
Both, really. Can we actually design and build this thing with current tech? Is it doable within a reasonable time frame?
Mm-hmm.
And critically, can we produce it at a cost that airlines are actually willing or able to pay?
It makes perfect sense. Designing the fanciest plane ever is useless if it's impossible to build or if no one buys it. Okay, so idea checked, feasibility confirmed, then the design work starts properly, and I guess computers are just essential now.
Oh, absolutely essential. This is where CAD computer-aided design software really comes into its own. Engineers use these incredibly powerful tools to build detailed virtual models of the whole aircraft.
Like a digital twin.
Pretty much.
Yeah.
And it's not just the outside shape. It's meticulously designing everything. Aerodynamics, how air flows over it for lift, minimizing drag, structural design, making sure it can handle the immense forces in flight.
Every single curve, every angle, all mapped out digitally. But it's more than just the frame, isn't it? All the guts inside, too.
Precisely. CAD allows for total systems integration. You're designing how all the different bits work together seamlessly. The electrical systems, the hydraulics for things like flaps and landing gear, the complex avionics, that's the navigation, communication, flight controls, all integrated. They even use CAD for the interior layouts. Where do the seats go? The galleys, the lavs. It's all planned virtually.
Wow. It's
Yeah.
like designing a whole flying city inside a tube. I remember seeing pictures sometimes, small models of planes being tested somewhere. What's that about?
Ah, yes. You're thinking of wind tunnel testing. That's still vital.
Even with the fancy computer models.
Yep. Even with amazing simulations, physical testing is key. Engineers build these scaled-down models of the design and put them in wind tunnels with controlled airflow.
Okay.
This lets them physically measure things like drag air resistance and lift and check the overall stability. It helps validate the computer designs, spot issues, maybe find improvements before they commit to building a full-size prototype.
Got it. So virtual models, then miniature physical tests. Once the design is locked down through all that, finally time to actually build the thing. Which brings us to materials. Can't just be any old metal, I imagine.
Definitely not.
Yeah.
Modern aircraft need this incredible combination. It's
Yeah.
super lightweight, but also exceptionally strong.
Right, because every extra bit of weight costs fuel.
Exactly. More weight means less efficiency. But at the same time, the airframe has to withstand huge stresses during flight, turbulence, landings. It needs to be incredibly robust.
So what kind of advanced materials are we talking about here?
Well, aluminum alloys are still a big part of it for the mainframe and the skin on many planes. Good strength to weight ratio, relatively speaking.
Okay.
But you're seeing more and more advanced stuff. Titanium, for instance, it's super strong, handles high temperatures really well, so it's great for engine parts, areas near the engines.
Uh-huh.
And then there are carbon fiber composites. These are amazing, exceptionally light, incredibly strong. They're used now for major parts like wings, big sections of the fuselage, especially on newer planes like the Dreamliner.
Composites. That sounds really high tech.
It is. It's really changed what's possible in aircraft design and performance. Lighter planes, different shapes are possible now.
No, I've often heard that different bits of one plane are actually made all over the world. Is that true?
Oh, absolutely.
Hmm.
Building a modern airliner is a truly global effort. It's quite something.
Like what parts where?
Well, for example, the wings for a particular model might be designed and built in the UK. Large chunks of the fuselage could be made in France or maybe the US. And then the engines. They often come from specialists like GE or Rolls-Royce, regardless of where the main assembly happens.
So it's this massive international jigsaw puzzle just to build one plane? How do all these huge pieces made in different countries actually get brought together for the final assembly?
That's a whole logistical feat in itself.
Hmm.
These enormous, often quite delicate components are shipped sometimes by sea, sometimes by specially designed cargo planes like the Beluga.
Ah, yeah, I've seen pictures of that. Looks like a whale.
Exactly. They're carefully transported to these huge final assembly facilities.
Huh.
I think Boeing's place in Everett, Washington is one of the largest buildings in the world by volume, or Airbus's main site in Toulouse, France.
Must be incredible to see inside those places. So all the giant parts arrive. What's the next step on the assembly line?
Well, it's a very carefully planned, almost choreographed sequence. It often starts with building up the fuselage.
Yeah.
You have these large barrel-shaped sections that get precisely joined together.
Right.
Then a really critical stage, wing integration. Attaching those massive wings to the fuselage, it needs incredible precision. They use heavy-duty bolts, strong structural adhesives. It has to be an absolutely solid connection.
I bet. A tiny misalignment there could be a huge problem down the line.
You wouldn't want that, no. After the wings, the tail section goes on the horizontal and vertical stabilizers at the back. Then, installing the landing gear, that's not just the wheels and struts, but all the complex hydraulic systems to make them go up and down smoothly.
Okay.
And while all this big structural stuff is happening, teams are busy routing miles, literally miles, of electrical wiring throughout the plane, powering everything.
Wow, miles of wire.
Yeah. And finally, integrating the avionics and instruments, flight computers, radar, navigation gear, all the controls in the cockpit. It all gets connected and installed.
It really does sound like an unbelievably complex puzzle. Millions of pieces, all needing to fit perfectly. Okay, so after all that technical assembly, the plane exists structurally, but it's not ready for people yet, right? Needs an interior.
That's the next phase, exactly. Making the aircraft livable, as you might say.
So putting in the seats?
Yep. Bolting all the passenger seats to the floor rails, installing the overhead bins for luggage, fitting the galleys, the kitchen areas, and the lavatories.
And I guess all the passenger comfort stuff too, like screens and Wi-Fi.
Precisely. The in-flight entertainment systems, the cabin lighting, all the wiring for Wi-Fi gets put in. And of course, fully equipping the cockpit with all the instruments and controls the pilots need.
Okay, so we've gone from an idea on paper, or maybe a screen, to a nearly complete airplane. But surely, before it carries a single paying passenger, it needs some serious testing.
Oh, absolutely. Unbelievably rigorous testing. Safety and performance are just non-negotiable in aviation. So the testing and quality control phase is incredibly strict and thorough.
What does that involve? Kicking the tires?
It's a bit more than that. It starts with extensive ground testing. They check everything. Hydraulic systems, electrical systems, run them through their paces. Landing gear, cycle it up and down again and again.
Makes sense.
They pressurize the cabin, check for leaks, check the structural integrity. They run the engines up, test the throttle response, calibrate the fuel systems meticulously. It's a massive checklist.
Okay, so tons of checks on the ground. But then the bit everyone thinks of, actually flying it.
Yes, flight testing. That's the next crucial stage. Highly experienced test pilots, specially trained for this, take the aircraft up.
Must be quite a job.
It is. They really push the aircraft. Test its stability, how it handles different maneuvers. They evaluate engine performance at various altitudes and different conditions. They even deliberately practice emergency procedures to make sure everything works as designed and the crew can handle it.
Wow. Okay, so assuming it passes all those ground and flight tests with flying colors, What's the final hurdle before it can join an airline's fleet?
That's where the regulators come in. Aviation authorities like the FAA, the Federal Aviation Administration in the U.S., or EASA, the European Union Aviation Safety Agency.
Right. They have the final say.
They do. If the aircraft passes all those comprehensive tests and proves it meets their very strict safety and performance standards, these authorities issue what's called a type certificate. That's basically the official green light for that aircraft model to enter commercial service.
The ultimate stamp of approval. So certificate granted. Then what? Is it ready?
Almost. There are a few final steps. Usually the aircraft gets painted in the specific livery, the colors and design of the airline that ordered it.
Ah, the branding.
Exactly. After the paint job, there's another final, very detailed inspection, just to catch any last-minute snags.
Yeah.
And then the brand new plane is flown to the customer airline, either to their main base or a delivery center, and they officially take ownership.
What a journey, start to finish. You mentioned earlier, and it really struck me, how global this all is. So many countries, so many companies involved in just one plane.
It really is a triumph of global collaboration. It's amazing when you break it down. You might have landing gear designed and made in Germany,
Okay.
critical carbon fiber parts coming from Japan, sophisticated avionics from America, maybe the engines built in France or the UK, all these high-tech pieces converging. It really shows how interconnected the aerospace industry is.
Wow.
Specialist expertise all over the world.
It's absolutely mind-boggling when you actually stop and picture it. Do we have a fun fact that maybe drives home just how many bits go into one of these machines?
We certainly do. Think about the Boeing 787 Dreamliner, a very advanced aircraft.
Yeah.
That single plane is made up of over 2.3 million individual parts.
Wow. 2.3 million.
Million. And get this.
Yeah.
If you took all the electrical wiring inside it and laid it out end to end, it would stretch for hundreds of kilometers.
That's incredible. That really puts the scale of it all into perspective. Millions of parts, complex global supply chain, years of design and work.
Exactly. From that first concept maybe sketched out to seeing that fully assembled state-of-the-art airliner lifting off, it's just this epic fusion of science, incredible skill from countless people worldwide, and the seamless international teamwork.
So yeah, maybe the next time any of us are settling into our seat for a flight, it's worth taking just a second to appreciate the sheer complexity, the ingenuity that went into the machine we're sitting in. It really is a masterpiece of human engineering.
It truly is. And, it makes you wonder, what's next? What future innovations in design and manufacturing are just around the corner? And just thinking about the sheer logistical ballet required to bring all those precise, globally sourced parts together perfectly. It's a profound statement about what humans can achieve when they collaborate. You're looking out the window at the airport, or maybe you're craning your neck as one flies overhead, and it's hard not to notice. Airplanes are overwhelmingly white.
They really are, aren't they?
Ever stop to really wonder why that is? It turns out there's, a whole lot more to it than just a default setting.
Absolutely. What seems like maybe just a simple aesthetic choice is actually rooted in a fascinating combination of scientific principles, safety considerations, and even some pretty smart economic strategies.
Right. So for this deep dive, we've pulled together a range of information that really unpacks the reasons behind this, widespread preference.
Yeah, we looked into quite a bit of material on this.
And honestly, when I started looking into this, I was genuinely surprised by the clever science and practical thinking behind something as seemingly straightforward as the color of an airplane.
It's one of those things hiding in plain sight.
Okay, so let's get right into it then. One of the first things that came up is how these things handle the extreme conditions way up there in the atmosphere.
That's right. When you think about airplanes cruising at, 35,000 feet for hours on end, they're exposed to really intense solar radiation, much more than down here.
Because there's less atmosphere to filter it out.
Exactly, and this is where the thermal advantages of white really come into play. We all know darker colors absorb more heat.
Sure, basic science.
What's fascinating here is how significantly that impacts the aircraft itself. White, on the other hand, has a high albedo, basically. It reflects a large chunk of that incoming solar radiation.
So it doesn't heat up as much.
Precisely. It prevents that heat buildup.
Right. So if it's absorbing less heat, that's got to make a difference inside the plane. Not just for keeping passengers comfortable, but I guess for the equipment too, right?
Oh, absolutely critical for the equipment. That increased heat absorption by darker surfaces can put a real strain on the aircraft's cooling systems.
Right. They'd have to work harder.
They would. And over time, this constant cycle of heating up, cooling down, well, it can potentially lead to the premature degradation or even damage of critical components inside the plane's structure.
Hmm. Like wear and tear from temperature swings.
Kind of like constantly leaving your car out in the scorching sun versus parking it in the shade.
Hmm.
The effect adds up.
That makes a lot of sense. And it's not just when they're flying, is it? I mean, I've been stuck on some runways that felt like absolute frying pans. What role does the white play when they're just sitting there on the ground?
Exactly. Especially at airports in hot climates, a white exterior makes a big difference in keeping the parked aircraft cooler.
So it's not boiling inside before people even board.
Right. This reduces the need for running the auxiliary power units, the APUs, at full blast just to keep the cabin temp down, which, saves fuel and reduces wear and tear on those ground systems too.
It's like giving the plane its own personal parasol, sort of.
That's a good way to put it, a built-in heat shield.
So it's a built-in way to manage heat, both in the air and on the ground.
Yeah.
Okay. Now, beyond the science of temperature regulation, let's talk about something that always catches people's attention. The bottom line, painting a massive airplane cannot be a small expense.
You're absolutely right there. Painting an aircraft is a substantial investment. We're talking often ranging from $50,000
$50,000 just for paint.
up to maybe $300,000, depending on the size of the plane and, how complex the paint scheme is.
Wow. Okay, so that raises an important question.
Yeah.
How does choosing white contribute to potential cost savings then?
Well, there are a few ways. One of the points that came up in what we looked at is the actual weight of the paint itself.
The paint has significant weight.
It really does. Lighter white paint can contribute to overall fuel efficiency. Now, it sounds small, but even a few £100 difference.
A few £100 just from paint?
Yeah, it adds up. And that difference can have a noticeable impact on fuel consumption over the entire lifespan of an aircraft. When you're dealing with the massive fuel costs airlines face, well, every little bit of weight reduction helps their budget.
Okay, I can see that. Pennies add up to dollars, pounds add up to tons of fuel saved over years.
Yeah.
And then there's how long that paint job lasts, right? You wouldn't want to have to repaint these massive things constantly.
Exactly. That's another key point. White paint tends to hold its color and its reflectiveness longer than darker colors, especially when it's exposed to the elements up high.
You mean the intense UV light?
Precisely. That intense ultraviolet radiation at high altitudes really degrades darker pigments faster. So this slower rate of fading for white means white-painted aircraft don't need to be repainted quite as frequently.
Which saves money on the paint job itself and also less downtime for the plane.
Exactly. Think about the downtime involved in taking a huge jetliner out of service for a full repaint that has a real financial impact on the airline's schedule and revenue.
Definitely. Okay, and this next reason seems really practical, almost like a safety feature built right into the color itself, being able to spot problems easily.
Yes, this one's crucial for maintenance and safety. The high contrast of a white background makes it much, much easier to detect various forms of damage and leaks during inspections.
Okay, like what specifically? What are we talking about being easier to see against white?
Well, things like oil leaks, maybe hydraulic fluid leaks, even the subtle signs of bird strikes or small cracks developing in the aircraft's skin, they become far more visible against that plain white exterior.
Okay, so dark streaks or little dents would just pop visually.
They really do. And this ease of detection is directly linked to safety and efficiency. Imagine a tiny hydraulic leak starting somewhere. On a dark-colored plane, maybe it goes unnoticed during a quick pre-flight walk-around.
Right, blends in.
But on white, it would likely be starkly visible. Spotting that early could potentially prevent a much more serious malfunction down the line.
So because you can see these things more easily, you can fix them faster.
Precisely. Earlier detection of potential issues leads straight to increased safety and also, as you said, shorter maintenance turnaround times. If a problem is spotted early during just a routine visual check, simply because it stands out against the white paint,
Then you fix it then and there.
right, the aircraft can be repaired and back in service more quickly, minimizing flight disruptions and keeping the schedule running.
Makes total sense. Okay, now let's think about the airlines themselves and how they manage their fleets. It sounds like having a predominantly white plane offers some advantages when it comes to things like leasing and selling aircraft too.
It absolutely does. A white plane essentially acts as a kind of blank canvas. Think about it in the bigger picture of airline operations. Aircraft get leased, sold, and swapped between different carriers all the time.
Right, you see planes moving between airlines, sometimes still with traces of the old paint job.
Well, in those situations, having a predominantly white exterior is incredibly beneficial for the transition. It requires significantly less time and, crucially, less cost to repaint the aircraft with the new airline's livery.
Livery, that's the airline's specific paint scheme and branding, right?
Exactly. A white base coat just simplifies that whole rebranding process considerably for the new owners or the leasing company.
So it's really about providing flexibility and keeping costs down for the airlines when they're managing these, very expensive and complex fleets of aircraft.
That's a huge part of it, flexibility and cost efficiency in fleet management.
And I guess maybe a smaller point, but less overall repainting has a slight environmental benefit too, right? Less paint being used over the plane's life.
Over time, yes, that reduction in the frequency of full repaints does translate to a somewhat lower environmental impact. Less paint manufacturing, less solvent use during application. It's a factor.
Okay. Now, shifting gears a bit, let's talk about visibility in different conditions. It's not just about seeing damage up close during an inspection, is it? We're talking about seeing the whole plane.
No, definitely not just close up. The visibility of white aircraft extends to various operational scenarios. Think about low light conditions on runways and taxiways and, dawn, dusk, or maybe foggy or rainy weather.
Right, when it's harder to see generally.
A white or light-colored aircraft is inherently easier for ground personnel and traffic control and other pilots to spot on the ground.
That seems absolutely crucial for preventing ground collisions or runway incursions, stuff you definitely don't want happening.
Precisely. Ground safety is paramount. And then if you consider a rare and worst-case scenario, like an aircraft being forced down in an emergency landing,
Okay.
a white exterior significantly enhances its visibility for search and rescue teams.
Ah, easier to spot from the air.
Much easier, across a wide range of terrains and environments, whether it's against dense green forests, brown deserts, or the dark blue of the ocean. That high contrast against natural backgrounds can be absolutely critical in locating a downed aircraft quickly.
Wow. You wouldn't necessarily think about that when you're just booking a flight, but that makes a huge difference in those critical situations where every single minute counts.
It really can. It's a safety factor that works across multiple scales.
Now, this next point is interesting and maybe a bit more subtle. The potential psychological effect on passengers. Is that really a thing?
Well, it's considered a less direct factor, perhaps, but still something that designers think about. White, as a color, is often associated culturally with feelings of, say, cleanliness, spaciousness, maybe modernity.
Okay, yeah, I can see that association. Clean and new.
And this perception, even if it's subconscious, can subtly influence how passengers feel when they're boarding the aircraft and finding their seat.
So it's almost about creating a more reassuring or, pleasant atmosphere before you even properly get settled in.
That's the theory, exactly. The idea is that a bright white exterior might contribute to a feeling of openness, maybe reduce any latent feelings of confinement or claustrophobia during those initial moments of boarding and preparing for takeoff.
Interesting. Well, the interior design obviously plays a much larger role once you're inside.
Of course, cabin lighting, seat pitch, colors inside matter more for the flight itself.
But that initial visual impression when you walk up to the plane or see it from the terminal could be influenced by the exterior color.
It could set a subtle tone, yes.
Now, okay, we've been talking so much about white, 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 but we definitely see airplanes out there with all sorts of colorful designs. What's the story with those? Are airlines just throwing all these advantages out the window purely for branding?
That's a great question, and it highlights that airlines absolutely use colorful liveries. It's powerful for branding, for reflecting a national identity, or maybe for specific marketing campaigns.
Sure, you can picture them.
Think of instantly recognizable examples like Emirates' prominent gold accents, or Qantas's iconic red kangaroo tail, or the very distinctive blue of ANA in Japan.
Right, so they're not just ignoring all these practical benefits of white we've spent the last few minutes discussing.
Generally, no. What's interesting to note is that even with many of these vibrant and colorful designs, the aircraft often still have a predominantly white base coat underneath.
Ah, so the color is applied on top of white.
Often, yes. The colorful elements, the logos, the stripes, they're typically applied over that white foundation. This means the core benefits like thermal management from the white base and maybe easier manufacturing with a standard base are still largely in play.
Okay, that makes sense. So it's kind of the best of both worlds, allowing for strong visual branding while still leveraging those underlying advantages of white paint.
In many cases, yes.
But what about those airlines that go really all out with color, like Southwest's various colorful schemes or maybe AirAsia's bright red planes? They seem mostly not white.
Right. In those cases where airlines opt for much bolder, more extensive color schemes that cover a larger percentage of the aircraft's surface, there are potential trade-offs.
Such as?
Well, these more vibrant, darker liveries might require more frequent repainting to maintain their intensity and avoid looking faded, especially with that UV exposure we mentioned.
Okay, higher maintenance costs there, potentially.
Potentially. And the increased layers or different types of colored paint could add slightly more weight to the aircraft compared to a simpler, predominantly white scheme.
Ah, back to the weight issue.
Yeah, but it's important to note these weight differences from paint color alone are usually relatively minor in the grand scheme of an aircraft's massive total operating weight. It's a consideration, but maybe not the biggest one for those airlines prioritizing brand identity.
Interesting. So it sounds like there's always a bit of a balancing act involved between branding, cost, maintenance, and these operational factors.
Absolutely. Every airline weighs those factors differently based on their business model and priorities.
Now, before we wrap up, you mentioned a few quick facts earlier that really highlighted some of these points. Could you share one or two of those again? They were quite striking.
Sure. For example, it's pretty remarkable that the white paint used on aircraft isn't just any white paint. It's specifically formulated to be incredibly durable and resistant to fading, despite that constant, intense UV exposure they get at high altitudes.
Right. You mentioned that. It really speaks to the advancements in material science, doesn't it?
It really does. You don't often think about that level of specialized chemical engineering going into something as seemingly simple as paint.
No, you really don't. What's another interesting tidbit?
Well, the sheer amount of paint needed is quite staggering. For a large aircraft like a Boeing 747, we're talking about something like 90 gallons of paint just to cover the entire exterior.
90 gallons. Wow.
And all that paint, as we touched on, adds up in weight. A typical paint job can add anywhere from, say, 600 to maybe 1,200 pounds to the aircraft's overall weight.
600 to 1,200 pounds. That really puts the weight factor and the potential fuel savings, even small ones, into perspective.
It absolutely does. Every pound counts when you're flying.
And you also mentioned earlier that it's not just commercial airlines that largely stick with white, right?
That's right. It's worth noting that organizations like NASA, for example, and various military branches frequently use white paint on many of their aircraft, too. And for the very same core reasons we've been discussing, effective thermal management and optimal visibility in various conditions.
No. So same logic applies beyond just passenger jets.
Exactly. This widespread adoption across different sectors of aviation really underscores the fundamental practical advantages of this seemingly simple color choice.
Okay, so as you can see, the prevalence of white airplanes isn't just about what looks clean or, modern or what's cheapest off the factory line necessarily.
Not at all.
It's actually a really carefully considered decision, driven by this fascinating and actually very logical mix of scientific principles, crucial safety considerations, economic efficiencies, and maybe even those subtle psychological factors.
It truly is. What might seem like just a default or maybe a boring standard appearance is actually the result of a whole lot of smart engineering and practical considerations that impact everything from passenger comfort and safety right down to an airline's bottom line.
So that next time you spot a white plane against the blue sky, maybe take a moment to think about all the hidden engineering and the smart choices that went into that seemingly simple color.
Mm-hmm.
And really makes you wonder what other everyday things have such surprisingly complex and, well, logical reasons behind them, doesn't it? Think about it. These multi-ton metal behemoths just effortlessly slicing through the sky. It's something we see all the time. Yet if you really stop and consider it, it feels almost like defying gravity. You ever get that sense of wonder? Like,
Yeah.
how does that actually happen?
Absolutely. It's a testament to human ingenuity, really, built on a really elegant foundation of scientific principles. Today, we're going to dive deep into the core of what makes an airplane fly.
Okay.
We'll look at the fundamental forces and the clever design that turns this seemingly impossible idea into everyday transportation.
Exactly. Our goal isn't to drown you in, like, technical jargon, but to give you a real sense of the magic, the science magic, I guess, behind how these things stay aloft.
Yeah.
So let's start with the big picture.
Yeah.
What are the main players at work when a plane is in the air?
Well, okay, imagine a constant kind of tug of war happening around the airplane. There are four primary forces always in play: lift, weight, thrust, and drag.
Lift, weight, thrust, drag.
They're the fundamental reasons why an airplane can take off, stay airborne, and, land safely.
Okay, let's unpack each of these then. Lift, that sounds like the most crucial one, right? The thing fighting gravity.
Precisely, yeah. Lift is the upward force that directly opposes the airplane's weight. It essentially pushes it skyward. Without enough lift, the plane simply wouldn't get off the ground or stay in the air.
Got it. The upward push.
Well,
Makes sense. And weight, that's just gravity doing its thing, pulling everything down.
exactly that. Weight is the force of gravity acting on the mass of the airplane, pulling it directly downwards. It's the force that lift has to overcome. Simple as that.
So it's a constant battle then. Lift versus weight. What about what makes the plane actually move forward? Is that thrust?
That's where thrust and drag come in, yep. Thrust is the force that propels the aircraft forward through the air. It's the power generated by the engines, basically.
The engine's working overtime to push us forward. Gotcha.
Yeah.
And drag is the thing that tries to hold it back, like air resistance.
Correct. Drag is the resistance the airplane encounters as it moves through the air. It's the aerodynamic friction that opposes thrust, trying to slow the aircraft down. Ah, okay.
Think of sticking your hand out of a moving car window, the push you feel.
Yeah.
That's drag.
Right. Okay. So for a smooth flight, it's all about balance. Lift needs to equal weight, more or less, and thrust needs to equal drag. Now, the really intriguing part for me is how we actually generate that lift. What's the secret sauce there?
The secret. Well, in large part, it lies in the shape of the wings. Airplane wings have a very specific cross-sectional shape called an airfoil. Have you noticed how the top surface is curved while the bottom is generally flatter?
Yeah, I've definitely seen that curve. What does that shape do to the air flowing over it then?
Okay, here's where it gets really fascinating. As the wing moves forward through the air, that curved upper surface forces the air traveling over the top to move faster than the air flowing along the shorter, flatter bottom.
Faster over the top, okay.
Now, there's a principle in physics, Bernoulli's principle, which, well, in simplified terms, tells us that faster-moving fluids, and air is a fluid, exert lower pressure. Oh, interesting. So faster air on top means lower pressure up there, and the slower air underneath means higher pressure.
Exactly, you got it. This pressure difference, higher pressure below pushing up and lower pressure above kind of sucking up, creates a net upward force on the wing.
Wow.
It's as if the higher pressure is literally pushing the wing upwards. That's the fundamental way lift is generated.
That's incredible, just the shape causing that pressure difference. Huh. I've also heard about something called the angle of attack. How does that fit into the lift equation?
Right, the angle of attack. It's basically the angle between the wing itself and the direction the air is coming from, the oncoming flow.
Okay.
If a pilot slightly tilts the leading edge of the wing upwards, it intercepts the airflow at a greater angle, and this can increase the amount of lift generated, but only up to a point.
Like holding your hand out that car window again and tilting it up slightly, you feel more push upwards.
Precisely that analogy. You feel more upward push.
But I bet there's a limit, right? You can't just keep tilting it up forever.
Absolutely. There's a critical point. If the angle of attack becomes too steep, the smooth flow of air over the top of the wing gets disrupted. It breaks away, it becomes turbulent, and the wing suddenly loses its ability to generate lift effectively. This is what's called a stall. And it's something pilots are, of course, extensively trained to avoid and recover from.
Right, a stall. Okay, that makes sense. So the wings are doing the heavy lifting, literally, to get us up. But what about moving forward? That's all on the thrust, right, from the engines.
Precisely. Thrust is the force that overcomes drag and propels the aircraft forward. And moving forward is essential because it keeps air flowing over the wings to generate that crucial lift.
Makes sense.
And the way thrust is produced, well, it varies depending on the type of aircraft. You've got jet engines, propellers, and even turboprops, which are kind of a mix.
Let's talk about those jet engines for a second. The roaring powerhouses on commercial planes.
Yeah.
How do they actually create that forward push? It's pretty amazing.
It is. The core process involves first sucking in a huge volume of air at the front. Then inside the engine, that air gets compressed to extremely high pressure.
Okay. Compressed air.
Then fuel is injected into that compressed air, and the mixture is ignited. Boom. This creates a rapid expansion of very hot gases.
Like a controlled explosion.
Pretty much. These high-speed gases are then blasted out the back of the engine at high velocity.
And that blast of air backwards creates the push forward. That sounds exactly like Newton's third law, right? Action, reaction.
You've nailed it. That's exactly it. The engine pushes the exhaust gases backward with great force,
Action.
and in reaction, the exhaust gases push the engine and therefore the entire airplane forward.
Reaction. Cool. What about propellers on smaller planes?
Simpler aircraft often use propellers, yeah? These rotating blades are actually shaped like little airfoils themselves. They work by grabbing a large mass of air and pushing it backwards.
Ah, like a fan, but much more powerful.
Kind of, yeah. Pushing air back to move the plane forward. And turboprops. They essentially use a jet engine not for direct thrust, but to spin a propeller very efficiently. It combines some benefits of both systems.
Interesting. Okay, so lift gets us up, thrust moves us forward. Now for that invisible foe you mentioned, drag. What are the different ways an airplane experiences this air resistance?
Right, drag. It's the force that always opposes the airplane's motion through the air. Think of it as aerodynamic friction, trying to hold the plane back. We generally categorize it into two main types.
Right, what are they? Lay 'em on me.
Okay, first, there's what we call parasite drag. This is basically the resistance caused by the airplane's shape and the friction of the air moving past all its surfaces.
Like the body of the plane, the fuselage.
Exactly. The fuselage, the wings themselves, not the drag related to lift. We'll get to that landing gear if it's down. Even tiny things like rivets and seams add up.
So it's just the cost of pushing anything through the air?
Pretty much. It's like trying to push a brick through water versus a smooth, streamlined shape. The brick creates much more resistance, more parasite drag.
That makes sense. So all that sleek, smooth design we see on modern planes is about cutting down this parasite drag as much as possible.
Absolutely. Minimizing parasite drag is crucial for efficiency.
Okay, what's the other type then?
The second type is called induced drag. Now, this one's a bit more interesting because it's actually a direct byproduct of generating lift.
Oh. How does that work? The thing keeping us up also holds us back.
Kind of, yeah. Remember how the higher pressure air below the wing wants to move towards the lower pressure area above the wing?
Uh-huh.
Well, at the wingtips, this pressure difference causes the air to curl around from bottom to top, creating swirling masses of air called wingtip vortices.
I think I've seen photos of those, like little tornadoes coming off the wingtips.
Exactly like that. These vortices disrupt the smooth airflow behind the wing, and, well, they create drag. It's an unavoidable consequence of the wing producing lift. You can't have lift without generating some induced drag.
Huh. So the very process that keeps us in the air also creates its own form of resistance. That's a fascinating trade-off.
It really is. And aircraft designers are constantly working to minimize both types of drag. For instance, those upward curving tips you often see on modern airliner wings.
Yeah, winglets.
Winglets, exactly. They're specifically designed to disrupt those wingtip vortices and reduce that induced drag, which saves fuel.
Clever.
No.
Okay, so we've covered the four fundamental forces: lift, weight, thrust, drag.
Yeah.
Now, how does a pilot actually maneuver this incredible machine? How do they control where it goes, make it turn, climb, descend?
Right, control. That's where the control surfaces come in. These are essentially movable parts, mostly on the wings and tail, that allow the pilot to change the airflow in precise ways.
Okay.
This gives them direct control over the aircraft's attitude, its orientation in the air, and its direction.
Let's go through the main ones. I know there are ailerons out on the wings. What do they do?
Ailerons, yes. They're usually located on the trailing edge, near the wingtips. They work in opposition. When the pilot moves the control stick, or wheel left, the left aileron goes up and the right aileron goes down.
Opposite movements. Okay, what does that achieve?
Well, the aileron going down increases lift on that wing, while the one going up decreases lift on the other wing. This difference in lift causes the airplane to roll or tilt from side to side.
Ah, so that's how they bank into a turn.
Exactly. Rolling initiates the turn.
Okay, ailerons for rolling and turning. What about pitching the nose up and down? That's the elevators, right? On the tail.
Correct. The elevators are on the horizontal part of the tail, the horizontal stabilizer. When the pilot pushes or pulls the control column, the elevators move up or down together.
Pushing forward makes them go down.
Typically, yes. Pushing forward lowers the elevators, which pushes the tail up, causing the nose to pitch down. Pulling back raises the elevators, pushes the tail down, and makes the nose pitch up.
So that controls climb and descent. Pitch up to climb, pitch down to descend.
Precisely. It controls the airplane's pitch attitude, which is key for managing altitude.
Got it. And then there's the rudder on the vertical tail fin. What's its job? Yaw.
Yes, the rudder controls yaw. It's on the vertical stabilizer and is controlled by pedals the pilot uses with their feet.
Feet control the rudder.
Okay. Moving the rudder left or right causes the nose of the airplane to swing, or yaw, left or right around its vertical axis. While the ailerons roll the plane into the turn, the rudder is used to coordinate the turn smoothly.
Coordinate. How so?
It helps keep the nose pointed in the direction of the turn and prevents the plane from kind of skidding sideways through the air. It keeps things nice and tidy.
Okay, so ailerons roll, elevators pitch, rudder yaws, and finally, flaps.
Wow.
I always see those big panels extending from the wings during takeoff and landing. What's their specific job?
Ah, flaps. Yes, very important. They're also on the trailing edge of the wings, but usually closer to the fuselage than the ailerons. When the pilot extends the flaps, they effectively increase the wing's curvature and surface area.
Increasing curvature, like making the airfoil shape even more pronounced.
Exactly. And doing that increases both the lift and the drag the wing produces.
More lift ADA, more drag. Why would you want more drag?
Well, think about takeoff and landing. You're at lower speeds. The extra lift from the flaps allows the aircraft to fly safely at these slower speeds without stalling.
Ah, okay. More lift at low speed is good.
And the extra drag, that's actually helpful for landing because it allows the plane to descend more steeply without picking up too much speed, and it helps slow the plane down after touchdown.
Right, so flaps are crucial for low-speed flight phases. Okay, so it's this really intricate dance of all these surfaces working together controlled by the pilot. Can we just quickly, walk through a typical flight from takeoff to landing and see how all these pieces, lift, thrust, drag, controls, come together?
Absolutely, let's do that. So, for takeoff, the pilots line up on the runway. They'll typically set the flaps to a specific takeoff position for that extra lift.
Okay.
Then they apply full thrust from the engines. The plane accelerates rapidly down the runway. As it reaches its calculated takeoff speed, the lift generated by the wings becomes greater than the aircraft's weight.
And up it goes.
And up it goes, lift off. During the climb phase, the engines are still providing significant thrust, and the pilots use the elevators to maintain a steady climb angle, pitching the nose up.
Climbing up to that cruising altitude.
Right. Once they reach the desired cruising altitude, say 35,000 feet, they reduce the engine thrust. Now, the goal is balance. Thrust is adjusted to exactly counteract drag, and lift perfectly balances the weight.
So it just cruises along, stable.
Exactly. Nice, smooth flight, hopefully.
And then eventually, coming back down.
For the descent and landing, it's sort of the reverse. Pilots reduce the engine thrust significantly, so drag starts to overcome thrust, and the plane slows down and descends. They'll often extend speed brakes or spoilers on the wings to increase drag further if needed.
Okay.
As they approach the airport, they'll extend the flaps in stages and lower the landing gear. Both add considerable drag and allow for stable flight at the slower landing speed.
Flaps and gear down. Check.
They use the elevators to control the descent path, the rate of descent. Then, just before touchdown, a final flare maneuver using the elevators raises the nose slightly for a smooth landing on the main wheels first, usually. Then they use brakes and reverse thrust to slow down on the runway.
Wow. It's amazing how all these forces and controls have to be in such perfect harmony, constantly adjusted. It really gives you a whole new level of appreciation for the engineering and the piloting skill involved.
It truly does. It's a constant balancing act. And just to give you a little more perspective on the scale we're talking about, here are a couple of, I think, fascinating facts about flight.
Oh yeah, go on.
Did you know that the average commercial airliner typically cruises at an altitude of around 35,000 feet? That's nearly 7 miles, or about 10 kilometers, straight up.
Wow, it's 7 miles. That's way up there. It really feels like you're just floating sometime.
It does. And consider the sheer weight of these aircraft. A large plane, like a Boeing 747, its maximum takeoff weight can be over 400,000 kilograms.
400,000 kilos. That's
Yeah.
over 880,000 pounds. Hundreds of tons.
Hundreds of tons, exactly. It's almost mind-boggling that something so incredibly heavy can not only get airborne, but stay up there and fly so smoothly for hours on end.
Absolutely incredible. Next time I'm looking out the window on a flight, I'll definitely be thinking about all this. Lift, drag, thrust, weight, airfoils. It's not some magical force keeping us up. It's just really, really smart science and engineering in action.
Precisely. You're essentially sitting inside a massive metal tube, right? Being held aloft by the very air it's pushing through, powered by controlled fire, essentially, in the engines, and precisely guided by these fundamental laws of physics and aerodynamics. It's a truly remarkable achievement of technology.
It really, really is.
Yeah.
Thinking about this incredible feat, this whole deep dive, it makes you wonder, what other seemingly everyday marvels around us are also based on these same underlying principles. Balanced forces, clever fluid dynamics, smart design. It's definitely food for thought.
Thanks for breaking down the science of flight with us today.